Right. So, in our subject selected topics in decision modeling, we are now in our 40th lecture, that is NSGA 2 examples. So, in our previous lecture we have seen how to carry out multi objective optimization with regard to evolutionary computing meta heuristic technique, and we have taken up one such technique called NSGA 2, and I have discussed the general ideas of NSGA 2. So, today's lecture we shall understand that with examples. So, let us take a very ordinary and simple problem. Supposing there is a right circular cone, and this right circular cone is we have to design with minimum possible total area and minimum possible lateral surface area, obviously with regard to certain constraints of the height and other things, height and the radius. So, these are the things: r is the base radius, h is the height, v is the volume, sh is the slant height which is given by root over r square plus h square. Then b is the base area which is pi r square, it is the base area. Then s is the lateral surface area, that is pi r into sh, sh and pi r, and T is the total area, that is B plus S. So, pi r, r plus sh is all right. So, our job is to really design means taking an r and taking an h that will minimize s and minimize t, is all right. So, that is our example problem. So, very simple problem really, but then let us see, we have taken a non-trivial, I mean rather trivial kind of input values, that is r is between 0 and 10, h is between 0 and 20. You may think that if r equal to 0 and h equal to 0, that is the best possible solution. You are right, but then let us, we have taken this simple problem essentially to really understand that how NSGA 2 tries to do this with regard to the minimization of S and minimization of T. It is good that if we also have an idea about the ultimate optimization solution, right. So, let us take some random population. So, we have taken, let us say 6 random parent population, and these parent populations are randomly obtained. So, 10 and 19.61, 4.99 and 5.1, 6.09 and 0.79, etc. So, these are our initial random parent population. So, in order to carry these out, first of all we have to encode this. If you recall our GA discussions, then the first thing is to encode. So, the encoding requires r is between 0 to 10 and h is between 0 to 20. So, you can say that b minus a, I mean b and a is 0 for r 0 10, a is 0 and b is 10, right. So, 2 to the power m minus 1 to 2 to the power m should be b minus a into 10 to the power 2. So, you can see b minus a in this case is 1000, right. So, because we need 2 digit accuracy, that is why 10 to the power 2. So, supposing we need at least 2 digit accuracy. So, we need to have 1000 points between the binary should represent at least 1000 points. We know that 2 to the power 9 is 512 and 2 to the power 10 is 1024, is it not? We know that. So, we know that 512 and 1024, within that 1000 lies. So, to represent 1000 because we want 2 digit accuracy. So, we should represent 1000 different combinations. So, we must have m equal to 10, all right. Similarly, for h, which is between 0 to 20, we need 2000 representations. So, we must have 1024 to 2048, where this one is 2 to the power 10, this one is 2 to the power 11. So, we therefore, we need 10 bits for A and 20 bits for B. Now, there are different ways of doing it. So, the kind of things that we have done is this, that we represent these 6 values in such a manner that first 10 bits represent R. So, this is going to be R and this is going to be H. This is R, this is H. Now, you see, in the first 10 bits all ones means what? Is it 1024 or 1000? What we have done? We have taken all bits as 1000. We have, that is how we have represented. Is it all right? So, because if you recall, let us look at the kind of solutions that we had taken. You see, R is exactly 10, right. So, we have to represent exactly 10s. So, all bit 1 we take as 10 and not 10.24, is all right. So, therefore, all other values will be like that. So, that means, we are really taking 1000 by 1024 as our accuracy, is all right. So, that is our accuracy. So, this ratio should be multiplied with, so really speaking this number is really 1024 all ones for R. So, this is 1024 multiplied by this ratio makes it 1000. So, that is how we encode. So, we have encoded each of these strings. So, 21 bits to each chromosome and that is our parent population. So, this is our parent population. What next? Next is we should do crossover and mutation. So, arbitrarily through a random number technique, we consider 0.25 crossover probability and randomly select 1 point crossover position, right. So, if 0.25 crossover probability and we choose some crossover point. So, supposing we choose actually crossover point here, right. So, supposing we choose our crossover point here. So, you see the first string, the first 5 is retained, rest 1 is coming from another string. So, you already know how to do crossover, we have discussed in detail. So, assume that after crossover we have generated these strings after the crossover operation. And then also we plan to do what is known as the mutation. For mutation, what we do? We have a 0.01 probability for mutation and randomly selecting the bits for mutation. So, let us say for these numbers, we have taken certain values and those values. So, this is the representation. So, we do some mutation, after mutation certain zeros and ones are changed based on the probability that we obtained, and then we get a set of 6 feasible solutions which we can then call as our offspring population. So, what we have done? We have started with a representation, that is called encoding, then we have done crossover and we have done mutation, and after doing crossover and mutation we have got the offspring population. So, essentially we have now got 6 parent population and we have got 6 offspring population with different S and T values. See, minimum our main purpose is that what is our objective function? Minimize S and minimize T. So, that is what is our objective function. So, our objective function is minimize S and minimize T. So, this is our parent population. Through the crossover and mutation, we have got the offspring population, and we have listed the S and T for the parent and S and T for the offspring with a purpose of minimize S and minimize T. Now, recall that the total population we have now is 12 strings. So, if we call them as strings or chromosomes, and again another set of strings or chromosomes for offspring, a total of 12 strings are with us. How many are we going to have in our next generation? 6 of them. So, we have to choose. Question is, how do I going to choose them? Out of these 12, which are going to go to the next generation? Had it been ordinary kind of genetic algorithm, the offspring population will become our next generation. Recall that. So, parent population is generation 1, offspring population is generation 2. Sometimes a little bit elitism is done where we do not take all 6 or we do not do so many crossover and mutation, we do maybe for 4 and 2 we directly bring from parent population, the best ones. But here we do not do that. From the 6 parent population we generate the 6 offspring, and out of all the 12 we try to get the non-dominated solutions into our next generation. So, like the example we have shown in our previous lecture, so out of these 12 we have to choose 6 solutions which are best possible non-dominated ranks, right. If I get 6 in the non-dominated, the Pareto optimal solutions in the first this thing itself, obviously we take those 6, it is very simple. But if that is not there, then what should we do? Let us see that. So, this is what we have got. Supposing we plot. So, these are our 12 values, these are our 12 strings, and this is what is our plot. So, if you plot, then you see that string 1 to 6 belong to the parent population and 7 to 12 belong to the offspring population. We need to choose 6 strings for the next generation. So, from the plot, can you see that 8 is best with regard to S and with regard to T? Can you see that? You know, which one is the minimum S? That is this one. Which one is the minimum T? This one. So, in the plot also, the Pareto optimal front will be like this. So, you can call it as the front 1. Now, if I take out 8, right, if I take out 8, then which one is the best possible solution which minimizes both S and T, right. Then again you see that is 2. So, 2 will be in the front 2, then it will be 3. So, that will be the front 3, is it all right. So, like this, you know, we have to go ahead and find the Pareto optimal fronts, because had it been only one choice, there is no doubt that 8 is the best solution, and in the first front only 1 is there. Why only first front 1 is there? Because it is best from both counts, is all right. But only one will not do, we need to have more. So, we choose the taking out 8, which one will form the non-dominated. So, rank 2, that is the front 2, then we will have something. what is in the front 3, what is in the front 4, front 5, like this we have to really do that. So, that is how we should choose the 6 strings for the next generation, right. So, let us see the procedure. The procedure we follow is this. So, we really combine say 1 versus 2. So, if I compare, that is how to begin, that is the process actually, because everything has to be implemented in computer, a computer based solution has to be obtained. So, this is how the solution is done. So, if I compare 1 and 2, I see that the values of 2 is better than 1, is it not. So, if you compare S and T, then 2 dominates 1, is it all right. So, since 2 dominates 1, 1 will be replaced by 2, all right. So, that is what is the 2. Then similarly, if I keep on comparing, the 2 dominates 3, 4, 5, 6 and 7, but 8 dominates 2. No, if I compare 2 and 8, so this is 2, so this is 2, but this is 8, we see that 8 dominates 2. So, 2 is replaced by 8 and the sorting continues. 8 also dominates 9, 10, 11 and 12. So, therefore, the first non-dominating front is 8, right. The first non-dominated front will be 8. So, we have got 8, we have seen graphically also that 8 comes in the top. So, that is the first, that is the front one. Then after that we continue and again we see that 1 dominates, that is 2 dominates 1 and 2 also dominates all the others. Obviously, 8 is gone because 8 has been formed of the first front. So, 2 dominates 3, 4, 5, 6, 7, 9, 10, 11, 12. So, second non-dominating front will be 2, is all right. So, we have got 2 non-dominated fronts, that is 1 and 2, right. Now, 3, if I see 3 dominates 1 and 3 also dominates all the others. So, it is coming exactly true. You recall what I said, that 8 comes first, then 2, then 3. So, 8 is in the front 1, 2 is in the front 2, 3 is in the front 3. You see, it is not like in the previous example where we got 4 of them in the first front itself. Here it is not like that. 8 is a clear winner, and taking out 8, 2 is a clear winner, taking out 2, 3 is also a clear winner. So, that is the front 1, front 2 and front 3. So, we got 3 fronts, but then we need 6 of them for next generation. Recall that we had 12 here, 6, first 6 are parent, next 6 are offspring. Out of 12, 6 will go to the next generation. So, even if we take first front, second front, third front, we have got only 3, we need 6 of them. So, again we continue leaving out those 8, 2 and 3. So, you see 4 dominates 1, 4 and 5, but if we compare 4 and 5, look here, the 4 and 5, 4 is better than 5 in S, but 5 is better than 4 in T, right. So, that is what we see, that between 4 and 5 there is no winner. So, they form a non-dominated set, is all right. So, 4 dominates 6, 7, 8, 9 and 8 is not there obviously. So, this is a mistake. So, there is no 8. 4 dominates 6, 7, 9, 10, but cannot dominate 11, although 4 is better than 12. So, look at 4 and 12. So, 4 is definitely better than 12. So, 4 is better than all others excepting 11. Compare 4 and 11. So, where 4 is better than S, but 11 is better than 4 in T. So, 4 dominates 6, 7, 9, 10, but 11 dominates 5 and 4 does not dominate 11. So, all these facts really point to the fact that that at the next this thing, the fourth non-dominating front will be 4 and 11, is all right. So, because 4 is better than all, but 4 and 11 they are forming a non-dominated set, is all right. So, that comes to the fourth non-dominated front, that is 4 and 11. Again we see the remaining ones. So, you see all the rest are taken out. So, we have now 1, 5, 6, 7, 9, 10, 12. So, again the same procedure, we see that 1 dominates 5, right, 1 is now better than 5, is the opposite, the 5 dominates 1, right, that is the 5 is better than 1. So, just opposite, 5 dominates 1, then 5 and 6 are non-dominated sets because of their values, and then further we see that 6 dominates 7, 9 and 10. So, we finally find that at this stage 5, 6 and 12 they form the non-dominating front, is all right. So, what exactly it means? It means that we have been able to find out this, that out of these S and T we have this one, and the first rank we have got 8. So, this is in the front 1. In the front 2 we have got 2, in the, that is F2. In the third Pareto front we have got 3. In the fourth one we have got 4 and 11, and in the fifth, obviously the relative positions may not be exactly what I am drawing, but something of this sort, right. So, now how many of them? 1, 2, 3, 4, 5, 6, 7, 8 are now candidates. How many should be chosen? 6. Now, obviously the first thing to choose is rank, the rank should be best. So, rank, the 8 has got the first priority, 2 is the second priority, 3 is the third priority, then 4 and 11 has the fourth priority. So, that makes 5. We need one more. Question is, between 5, 6 and 12, which one should we choose? That is the question, which one? Is all right. So, they will form the new population, that is the question. So, again now recall what we have to do now, we have to check the crowding distance. So, to estimate the density of the solution surrounding a particular solution, we take the average distance of two solutions on either side. So, initialize the distance to be 0, then for each objective M, sort the solutions in front in that given front and assign infinite distance to boundary values, and that is the first task, assign infinite distance to the boundary values. And for the others, this calculation I have already told you that for each solution find the adjacent values with regard to every objective function, and then the difference between the objective function value of x I plus 1 minus x I minus 1 divided by the max x max minus x mean for that objective function, right. So, that will be the crowding distance with regard to that particular feasible solution with regard to that objective, and then add for all such objective functions, that will be the crowding distance. So, choose first by rank and then by higher crowding distance. Why higher crowding distance? Because take the lonely ones, because the lonely ones, if you remove a large portion of the objective function space might remain unexplored, is all right. So, this is the essential idea, right. So, that is the conceptual thing. Now, the actual calculation. The question is between 5, 12 and 6, if you sort them in S and T, then you see that the best possible T belongs to 5 and best possible S belong to 296.8 belongs to 6. So, you see in a sense with regard to S 6 is boundary and with regard to T 5 is boundary. So, at least with regard to S 5 will be 6 will be given infinite score crowding distance, and with regard to T 5 will be given infinite score. So, infinity with anything will become infinity. So, therefore, the crowding distance for 5 is infinity, crowding distance for 6 is infinity. What is the crowding distance of 12? See the 12, which is the neighbor of 12? The neighbor of 12 in this particular front where only 3 elements are there, the neighbor of, see these are the 6, these are the overall S max and S mean, these are the T max and T mean, these are the overall values. So, what is for 12, what is the score for 12? The score for 12, you see with regard to S, this is 12, with regard to 12, the two neighbor values are 320 and 296.8. So, these two are taken, and what are the S max is 691 and S mean is 77.8, their difference is taken, right. So, this ratio is 0.037, and with regard to T, see 492.9, 492 more or less similar value by 9 minus 405 by this 1005.7 by 155.13, which are T max and T mean. So, if you take this ratio, we get 0.140, all right. So, if you add this and this, then you get the crowding distance of 12, right. So, crowding distance, therefore, you see the order is that 5 is the best, means highest crowding distance, 6 is equal to 5 and 12 is lower, right. Since distance values of both 5 and 6 are equal, any one can be selected for new population. So, supposing I choose say 5, all right. So, that will now form our new population. So, what is our new population? So, look here, this is our new population 8, 2, 3, 4 and 11. They are in the fourth front and then 5 is chosen. So, they will form our new population. So, you recall those Pareto fronts 8, 2, 3. So, they are all highlighted 4, 11 and F5 was 5, 6, 12. So, first of all the rank, these are having higher ranks, higher in the means lower rank value. So, F1, F2, F3, F4 they are chosen, and F5 only one. How it is chosen? Based on the crowding distance. Is it all right? So, when all of them are chosen, that completes one iteration of NSGA2 algorithm. Is all right? And stopping rule, maximum number of generations or no improvement in fitness value for some fixed number of generations. Is all right. So, this is how we carry out NSGA2. Now, very quickly I will show you a very important problem of a project management problem. So, this is a what is called a project management network diagram. So, there are 18 activities, and we have to, if we see really the combinatorial problem, we need to have the time and cost and quality. So, each one has got different options. So, combination is very high, it could be millions of combinations which are really possible. So, this is what we have see, this is how we carry out. So, population initialization, evaluate fitness, fast non-dominated sorting, calculate crowding distance, create child population, is all right, and then keep on going, is all right. Otherwise, combine parent population with child population, first non-dominated sorting of combine, create new population, last generation, next generation. So, this is how the method, already we have discussed exactly how it is done. So, this is our NSGA 2. So, these are the parameters, and this is the project cost versus quality plot that we have got, and cost versus project time trade off that we have got. Is all right. So, these are the kind of results, and if we see the results in the final results, then you see that time, cost, quality, time, cost, quality, all of these are, that is the kind of best solution that was obtained through the NSGA 2. So, you see large combinatorial problems can actually be solved by the NSGA 2 algorithm, right, all right. So, that is where we conclude, and we thank you very much for patiently hearing this lecture, right. So, thank you very much.